Welcome to the Universal Timeline. This is the complete history of the universe, episode 2 of 30. In the previous episode, we explored the Planck Epoch, the very first instant of time where our current understanding of physics breaks down entirely. Today, we move forward an infinitesimal fraction of a second to encounter a mechanism that is essential to our modern understanding of the cosmos. We are discussing cosmic inflation. The standard Big Bang theory, as developed in the mid-20th century, was incredibly successful at explaining an expanding, cooling universe. However, by the 1970s, cosmologists realized that the standard model left several critical questions unanswered. These puzzles suggested that something profound must have happened immediately following the initial moment of the universe's existence. The first of these puzzles is known as the horizon problem. When we observe the cosmic microwave background, which is the oldest light in the universe, we see that it is incredibly uniform in temperature, no matter which direction we look. The temperature of this background radiation is almost exactly equal, varying by only tiny fractions of a degree. This uniformity presents a significant problem for the standard Big Bang model without inflation. In the standard model, regions of space on opposite sides of the observable universe today have never been close enough to communicate with each other. Light has not had enough time since the beginning of the universe to travel from one side to the other. If these regions could never exchange heat or information, there is no reason they should have settled at exactly the same temperature. It would be a staggering coincidence for distinct, disconnected parts of the early cosmos to emerge with identical properties. The second puzzle is called the flatness problem. This relates to the overall geometry of space. According to general relativity, space can be curved by mass and energy, much like a sphere or a saddle, or it can be geometrically flat. Observations indicate that our universe today is incredibly close to being perfectly flat on large scales. The issue is that any deviation from perfect flatness in the early universe tends to grow significantly over time as space expands. For the universe to still be near flat today, billions of years later, it must have been exquisitely, precisely flat in its earliest moments. The required precision is so extreme that it suggests fine-tuning, something physicists generally try to avoid in fundamental theories. A third issue involves exotic relics. Grand unified theories in particle physics predict the creation of heavy, stable particles in the ultra-hot early universe, such as magnetic monopoles. If the standard Big Bang proceeded normally, these heavy particles should be abundant today, yet we have never observed one. To solve these problems simultaneously, physicist Alan Guth proposed the theory of cosmic inflation in 1980, which has since been refined by many others. Inflation is a period of exponential expansion that occurred very early in the universe's history. We are talking about a time far less than the blink of an eye after time zero. During this brief epoch, the universe did not just expand, it ballooned outward at a rate that is difficult to comprehend. In a fraction of a second, a region of space much smaller than a proton expanded to become larger than the entire currently observable universe. This brings us to the concept crucial to this episode's title: the universe expanding faster than light. It is a common misconception that nothing can travel faster than the speed of light. While it is true that no information or matter can travel through space faster than light, general relativity places no such limit on the expansion of space itself. During inflation, the space between points grew so rapidly that the distance between them increased faster than light could traverse that distance. Two adjacent points were effectively ripped apart from one another by the stretching fabric of spacetime. This rapid expansion provides elegant solutions to the puzzles we mentioned earlier. Consider the horizon problem regarding the uniform temperature of the universe. Before inflation began, the observable universe was packed into an incredibly tiny volume. At that minuscule scale, there was enough time for heat to disperse and equalize the temperature throughout that tiny region. Then, inflation occurred. It took that tiny, homogenized patch of space and stretched it enormously, far beyond the scale we can see today. The entire sky we observe is uniform because it all originated from the same tiny, causally connected patch before inflation blew it up. Inflation also solves the flatness problem. Imagine a balloon surface that is highly curved. If you inflate that balloon to the size of the Earth, any small section of its surface will appear perfectly flat to an observer standing on it. Similarly, the colossal expansion of cosmic inflation stretched out any initial curvature of space, making the universe appear geometrically flat today. Finally, inflation solves the problem of unwanted relics like magnetic monopoles. If these heavy particles were produced before inflation, the subsequent exponential expansion would have diluted their density immensely. They may still exist, but space is now so vast that encountering one has become statistically impossible. This is how inflation sets the stage for the universe we see today. as detailed here in the complete history of the universe. But inflation did one more vital thing. It did not just smooth the universe out, it also provided the seeds for everything in it. On the smallest quantum scales, empty space is a roiling sea of temporary fluctuations of energy. Normally, these fluctuations appear and disappear instantly on microscopic levels. However, during inflation, the expansion was so fast that these tiny quantum ripples were stretched across macroscopic distances before they could fade away. They became frozen into the fabric of spacetime as density variations. These variations meant that some regions of the early universe were slightly denser than others. After inflation ended, gravity went to work on these slight overdensities. The denser regions attracted more matter, eventually collapsing to form the first stars, galaxies, and clusters that make up the cosmic web. Without the magnifying glass of inflation, the quantum jitter of the early universe would have remained microscopic, and the universe would likely be a featureless, boring soup of particles. We know about these initial seeds because we can see their imprint today. The tiny temperature fluctuations we observe in the cosmic microwave background align with the predictions of inflationary theory regarding these stretched quantum ripples. Eventually, the mechanism driving inflation ran out of energy. The exponential expansion ground to a halt. The immense energy that was driving the expansion was dumped into the vacuum of space, creating a searing hot bath of particles. This process is known as reheating. At this point, the universe had been smoothed out, flattened, and seeded with the density fluctuations necessary for structure. It was now incredibly hot, dense, and expanding at a much more moderate, inertial pace. This marks the transition from the inflationary epoch back into the standard hot Big Bang model. In the next episode of the Universal Timeline, we will explore what happened immediately after reheating. We will enter the electroweak epoch and witness the fundamental forces of nature beginning to separate into the distinct forms we recognize today. Thank you for listening to episode 2 of the complete history of the universe.